Okay, hello everybody. I'm Richard Southwell, and I'd like to talk to you about a project I did on reproducing graphs. So, this is work that I did in the University of Sheffield a couple of years ago now, and some of it was joint work with Chris Cannings and Jonathan Jordan, who were also with the University of Sheffield. Okay then, so I suppose the first thing I should say is, what is a graph? Well, I use the terms graph and network synonymously, and basically a graph is just a load of dots, which we call vertices, connected by some lines, which we call edges. So there's obviously lots of examples of graphs in the world. I mean, examples of these graphs or networks include electrical networks, transportation networks, electronic networks, neural networks, nervous systems, respiratory systems. The large-scale structure of the universe can be thought of as a giant network. You can look at things like the cosmic web to find information about that. Small-scale physics, like chemical molecules, can be modeled as networks. Even fundamentally small physical systems can be modeled by quantum spin networks according to some theories. We have very large networks like the web or the internet or social networks. And then there are other various networks which are more abstract, like protein-protein interaction networks, or networks defining how different systems in language, how different words in language interact with each other. So there's lots and lots of examples of complex networks in the world, and I think more and more people are starting to understand that it's actually really important to find out things about complex networks. And so this whole new area of network science is growing up, and one of the main things that network scientists are usually interested in trying to do is finding good models for the development of various different kinds of complex networks. And so basically this is what this project is about. It's about a certain class of network development models. But before I go into those, I just want to say a couple of things about some famous network growth models which are very popular these days. And so there's a definite tendency to use probabilistic models to try and capture how complex networks arise. One of the first and one of the most popular models is the Erdos-Renyi random graph model. This is really a very simple idea. You take a set of vertices and you just randomly add some edges, so that, for example, you can say that you'll link any given pair of vertices with some fixed probability, say 0.5 or something like that. So the Erdos-Renyi graph model is really an extremely simple model for generating sort of randomly selected networks. And that was developed quite a long time ago, and I think it's been a very important and influential thing. I mean, a lot of good mathematics have been done by studying the Erdos-Renyi random graph model, and also I think it gave network scientists a good starting point for making more intricate kinds of models. Now, in more recent years, a couple of other probabilistic models have become very popular. Notably the Watt-Strogat small world model. So in this system you start off with a ring lattice, which is a very kind of regular network structure where every vertex looks kind of similar to every other vertex. And you take such a thing and then you do some random rewiring. So you just kind of unplug an end of an edge and plug it into somewhere else randomly and repeat that kind of thing a few times, and you end up getting what Watts and Strogatz call a small world network. And such a thing is fairly interesting because these small world networks tend to have some things in common with lots of complex networks in the real world. In particular, they have these features that they're kind of quite highly clustered, and they have these kind of cliquish properties they sort of look like they look like they have lots of community structures within them where everybody knows everybody, those kind of things. But they also have a relatively short graph distances between different pairs of vertices within. So if you want to get from vertex A to vertex B, you don't have to go across many edges to do that. Okay, I'm giving a very cartoonish outline of these models because, you know, it's not really the main subject of my talk. I just want to give you some idea of some of the previous models. Okay, so another one of these systems which is been quite well studied is the Barabasi-Albert preferential attachment model. And so again, this is a model which just captures a few of the key aspects of things which are present in real-world complex networks. So this model, basically, you start with a network and you add vertices into the thing one at a time. And when a vertex enters into the system, it's going to form some links with some pre-existing vertices. And the model is such that the probability that this thing is going to form a link with some vertex is just proportional to the number of connections that that vertex already has. Okay, so this Barabasi-Albert model has been very influential because it really captures this idea of the rich get richer, which is really a very kind of important effect in network formation. I mean, in social networks, you should probably notice that there are a few individuals who have massive numbers of acquaintances, whereas the vast majority of people have really relatively few acquaintances. And in fact, the Barabasi-Albert model gives various predictions about, well, you can derive formulas for the number of vertices you'd expect to see with different numbers of connections. And those kind of trends are mirrored quite well within certain real-world networks. Okay, so there are three probabilistic network growth models, which I think have been very influential over network science recently. And each of those are probabilistic, and what I want to talk about today is some deterministic network growth models. And I think that deterministic models, which don't have any sort of stochasticity, are not studied as much, but I think that there's some good reasons why it's important to look at such deterministic models. I mean, what I'm going to talk about is really a very kind of rich class of models which can be generalized in many different directions. And I think that this is one of the advantages of deterministic models. If you have a very nice, simple deterministic model that just captures what you're interested in, the fact is that you can extend it, you can generalize it, and you can make it probabilistic very easily. So, sort of conceptually, a nice, simple deterministic model acts as a very, very nice starting point, and it's often very easy to see how such a thing can be generalized in lots of different ways. And you should see as I talk that the kind of systems I introduce, I'll then show lots of ways that they can be generalized. So that's one thing. Another thing is, for example, if you're interested in where the complexity in a network comes from, using some kind of probabilistic model probably isn't going to be that beneficial, because in a probabilistic model, you don't really see where the complexity comes from. Basically, all of the complexity of a network generated by any of the three models, which I've discussed so far, just comes from the random number generators that work underneath those models. Whereas, if you have a deterministic model, you can see where every aspect of the behavior comes from, and you can see how and when complexity arises. And thirdly, it's often quite a lot easier to study deterministic models for a few reasons. I mean, practically, they are repeatable, and that is actually a very big deal. I mean, there's certain systems, certain kinds of these reproducing graph models, which I was amazed to find actually cause these complex self-replicating structures to occur. And had I been studying probabilistic models, I should have simulated them many times on a computer without watching what's going on, and I would have certainly missed any kind of phenomena like that. And even if I'd seen it, I would have assumed it was some kind of glitch, because probabilistic growth processes are not repeatable anyway, so anything that you see in them is really some kind of, it's not really a repeatable phenomenon. So practically they're easier to study because they're repeatable, and also they tend to be a lot easier to study mathematically. So this is that's a sort of brief introduction about how this work relates with the background. What about the actual systems? Well, basically the idea behind these systems is that we have a network which grows because the vertices within reproduce. Okay, so these models were really inspired by biological networks, things like ecosystems or social systems, where the individuals have offspring, and these offspring form interconnections with their parent surroundings. The basic inspiration is that, for example, if I have a baby, or if me and my wife have a baby, that baby is going to come into the world and it's going to form similar kinds of social relationships to the relationships that me and my wife have. In other words, when offspring are born, be they animal offspring or human offspring, or even more abstract things like a duplication of a website, or somebody imitating somebody else, or somebody joining somebody's position in a company. When these kind of offspring enter a network, they're going to form similar kinds of connections to their parents' vertices. And this is the inspiration behind the model. So this talk's going to be split up into three different parts. Firstly, I'm just going to talk about the pure reproduction model. That's where these networks just grow relentlessly because the vertices within inside reproduce. And so those models are fairly interesting because they really form the basis for the rest of the models. As I say, the other things are really generalizations of this pure reproduction idea. Also, these systems tend to be quite analytically tractable, so we can get a lot of nice results about what these systems do. But of course, these pure reproduction models are not particularly realistic, because in the real world, things don't just reproduce forever. I mean, things die, right? And that's why we consider lots of different generalizations. In particular, we think about what happens when we make our vertices mortal by imagining that they can only live for a certain amount of time. And that's what I call age-capped reproduction. And we'll see that when we add this kind of constraints, that these vertices die after a certain amount of time, we get much richer behavior. And we also get some interesting relationships with some models from population biology. Things like Leslie matrices and Fibonacci numbers appear in lots of different places. And on one hand, the systems are still quite well related to biological processes and things. And on the other hand, we are able to derive quite a lot of analytic results. And, it's quite a nice situation. And we also consider what happens when we add game theory into the system. So this is sort of a generalization in another direction, because we think that rather than assuming that our vertices die because they get too old, we assume that these vertices play games with each other, and the outcomes of these games affect which vertices die and which vertices get to reproduce. So I think these are really interesting systems, which are quite well poised to model lots of things in the real world. I mean, there's lots of places where we have these networks of individuals which form and take shape in ways that depend upon the strategic interactions of the individuals within. I mean, you can think about systems like the internet, economics, political systems, ecosystems. There's lots of these examples where there's kind of this two-way interplay between strategic interactions and the development and formation of networks. And I think that, you know, having these systems where the survival and reproduction of these vertices within this network depend upon strategic interactions is a really interesting way to study this idea. Okay then, so let me begin by talking about this pure reproduction models. So there's actually 8 different models of pure reproduction. And here's an example. So we have a graph structure here. These circles are the vertices, and this line here is just an edge, okay? So these are 2 linked vertices, and our model basically says that we're going to update the system again and again. So we're going to keep changing our network structure according to a rule. And this is the rule. Give every vertex an offspring with the same neighborhood as the parents. So let's apply this rule. This is the network we get. So what have we done here? Well, we've taken every vertex in our network and we've looked at what neighbors they have. So the neighbors of a vertex are just the vertices it's linked to. So we look at each vertex, we look at the neighbors it has, so there's just 2 here, and we give each of those vertices a child, an offspring, simultaneously. So these green vertices here are the offspring. And the idea is that these offspring here really kind of inherit their parents' neighborhood. They are linked to the same things as their parents were linked to. So this would be the network on the second time step. And then the idea is that we just keep updating the system again and again. We keep imagining that these vertices just carry on reproducing. And so this is the network on the next time step. And we can imagine the system continuing to evolve in this fashion. And so I think there are a few different systems which sort of work like this. You can think about, for example, on the internet, there'll be various different websites, and then there'll be other people who will come in and form similar kinds of websites to try and draw similar kinds of customers. And so you'll have this kind of cloning effect, which is pretty similar to this idea of new individuals coming in and forming links which are similar to the pre-existing ones. And so this system tends to be quite easy to study. So the degree of a vertex is just the number of neighbors that vertex has. And if we're interested in how the degree of these vertices, and so one thing that people are commonly interested in network science is how many vertices are there with a given number of connections. You see, this teaches you about things like how much equality there is in the system, and you know, you can compare the so-called degree distributions of various different kinds of networks. So how are the degrees of these systems distributed? Well, it tends to be quite easy to actually make a formula for that, because if you think about it, if you have a vertex of degree x, in other words, if you have a vertex of x connections, then when you update the system, that vertex is going to have an offspring who gets the same neighborhood as its parent. So that offspring is going to have x connections, but the parent on the next time step is actually going to have 2x connections, because it's linked to all the things that it was linked to before, and all of the things it's linked to before have now also had an offspring, which it's still linked to. So mathematically, it's really quite easy to describe how the degree distribution of these systems evolves. Okay, but these networks in Model 1, they have another very important feature. It turns out that really their dynamics can be explained very, very easily if one knows about some graph products. And so graph products, there's many different kinds of graph products. Basically, the idea is that rather like the way you can form the Cartesian product of 2 sets, and then you get the set of all pairs that have the first element in the first set and the second element in the second set. Rather like you can do the Cartesian product of sets, you can do the product of 2 graphs. And there's actually several different kinds of graph products which are defined. I'm going to talk about the Kronecker product. So let me see if I can. Okay, I'll give you a quick definition of the Kronecker product. If you don't understand it, don't worry, because it's not really a foundational part of this talk. So, don't worry if you don't understand it. But the Kronecker product of a pair of graphs, G and H, has a vertex set, which is the Cartesian product of the vertex set of G and the vertex set of H, and the edge set of this product graph is such that we'll have a pair UG UH and a pair of vertices UG UH and VG VH from this product graph are going to be connected if and only if UG and VG are linked in G and UH and VH are linked in H. Okay, so basically you have a pair of vertices are linked in a product if and only if the first vertices in their pair are linked in the first graph and the second vertices in their pair are linked in their pairs are linked in the second graph. Well, anyway, the point is that every time you update one of these systems here, every time you do this sort of operation where you give every vertex an offspring with the same neighborhood as its parents, it's basically equivalent to doing the Kronecker product of that graph with this funny kind of tadpole-shaped graph here. So, in other words, our basic updating step can kind of be replaced with this more mathematical operation of this mathematical operation of Kronecker producting with this network here. And the Kronecker product has various nice properties, which means that really viewing the system like this is quite a nice simplification. And in particular, we can really, what this means is that, in a sense, we don't really have to understand how arbitrary networks evolve under this rule. What do I mean by that? Well, back here, I show how an edge evolves under this rule. And they're the first few time steps. But what about if you have a different network, like a triangle or a square or something larger? Does one have to do fresh analysis for every new initial condition that one considers in this kind of system? The answer is no. The answer is basically that if you understand how one system runs under this model, you pretty much understand how every system evolves. And the reason for that is that basically, if you have an arbitrary graph G and you want to understand how it evolves under this model, what you can do is just evolve this network here, this funny tadpole-shaped graph. Say you want to know what happens when you run the thing for t time steps, okay? So if you run, starting from this tadpole-shaped graph, for t minus 1 time steps, and then Kronecker product what you get with this graph G that you're interested in, then you get the same thing as what you would have got if you just evolved G for t time steps. So really this feature that updating is equivalent to Kronecker producting with this gives you a nice kind of simplifying way to do things, and basically means that if you understand how this network evolves, you understand how pretty much everything evolves. So then the next question then, if you're interested in how these systems work, is how exactly does this thing evolve? Well, it turns out that it has quite a lot of nice features. In particular, there's some really nice symmetries which occur. So, we'll say a pair of vertices are automorphically equivalent within a graph. Basically, when those vertices look the same as each other. And more technically, if you can kind of swap around the labels of the vertices and basically transform one graph into the other, if there's an automorphism of a graph which sends one vertex to the other. And it turns out that, so if you quantify the probability that a pair of randomly chosen vertices are automorphically equivalent, what that's really telling you is, what are the chances that a couple of vertices that I pick randomly look the same as each other? So that's really a kind of quantification of how much symmetry there is in the network. Well, it turns out that when you evolve this system, you don't get a regular network, but you do get something which has quite a lot of symmetry. And in fact, this formula here gives you an exact description of what this probability of a pair of vertices being automorphically equivalent is. And it's quite a nice simple formula. Okay, so I haven't mentioned it here, but actually there's one of my favourite results which holds for this particular model. So I've showed a bit about the degree distribution, but I just want to talk about a very important feature of this model, and that is that when you evolve this system here, this kind of tadpole-shaped graph, you get a very large network, and it looks quite complicated, to be honest. It looks like it's got some kind of nested structure, but there's so many edges in there, but it's difficult to see exactly what's going on. Anyway, it turns out that using binary strings to keep track of the different vertices is a good idea. And there's lots of different analysis techniques you can use. But the actual network has a very, very interesting and quite surprising feature. And that is that if you take any graph at all, no matter how big or how complicated, that graph will appear as a kind of subgraph of the thing that grows when you evolve this thing for long enough. More precisely, if you have any graph which has m vertices, then if you evolve this network here for 2m squared time steps, you can find a subset of the vertices of that big structure that you get, and the subgraph induced on those vertices is isomorphic to whatever graph you had in mind. So, in other words, any structure, the structure of neural connections in your brain, or the structure of the social network of the world, or whatever, any kind of network structure you can think of will eventually be generated by this very simple rule as a kind of substructure. And that's kind of an interesting fact when you couple it with the fact that these systems are really quite easy to study. Okay, so that's just one of these pure reproduction models. Now I want to talk about another one. I call it Model 2, and it's a different idea, but it's quite similar. Once again, we suppose that every time step, every vertex has an offspring. But this time, we suppose that the offspring are only linked to their parents. So this is the system evolving over the first few time steps. And you see that we get this kind of tree-like structure. And we also, once again, have this kind of self-similarity, because really the kind of network which sprouts from any particular vertex is kind of like a time-lagged version of the original network which grows from the original vertex. So anyway, in total there are 8 different models, and this screen here sort of illustrates what all those different models are. Basically, the idea is that in every case we suppose that an update consists of giving every vertex an offspring. But what we vary is we vary the way that these different offspring are linked up. In particular, there's really 3 different kinds of edges which can be present within these models. There are, we assume that the pre-existing edges between parents always persist, okay? But we might have edges which link parents to their offspring, like in the last model I talked about, Model 2. So you can kind of think of those as umbilical connections, connecting mother and child or something like that. And we might also have these kind of edges which link which link offspring to their parents and neighbours. You can kind of think of those as sort of like uncle connections. And you might also have these kind of sibling connections here, or cousin connections, which link the offspring of previously connected parents. And so one can think of various different kinds of physical interpretations for these different models. As I've already said, this model 1 here can kind of be thought of as, in some sense, modelling social networks or animal ecosystems and how they develop, but also modelling things like the internet, where websites are duplicated. Or another thing is, for example, if you think about communication devices. For example, if new people buy mobile phones, they're going to use those phones to call similar people to the people that they called with their old communication devices. And so, in a sense, those new devices are going to have similar kinds of connections to the pre-existing ones. This model 2 here has a more kind of biological interpretation. In particular, if you think of these vertices as different females, then you link a female to their mother, and this is going to give you something like a kind of family tree showing how different individuals are descended from one another. I think this model 3 here is really a very good model for the development of social networks of reproducing individuals, because the offspring come into the world and then they form relationships with their parents, and also the individuals that their parents form relationships with. So it seems like quite a good model for quite a lot of things. Also, if you think about collaboration networks, I mean, if you're a professor and you get new students, that student's hopefully going to collaborate with you and the people that you collaborate with. Another model with a physical interpretation is this model 6 here. In this model, the offspring are linked to their parents and the offspring of their parents' neighbours. So you can think of this system perhaps as something. Well, I mean, think about mothers, daughters, and school buses. I mean, a new sort of daughter is going to make friends with their mother, but are also going to make friends with the daughters of their mother's friends. Perhaps they go to school on the same bus or something like that. So this model kind of captures the way the offspring of acquainted parents are going to probably become acquainted. Obviously, these are all deterministic and kind of abstract, but I think they form as a basis for more sophisticated models. I mean, one can easily make the birth processes or the linking processes probabilistic. But I think it's quite interesting to study the original models mathematically, because one gets some fairly interesting structures being developed. Okay, so you'll notice that I numbered all these models from 0 to 7. And I just want to tell you that actually the way that these models are numbered, it's kind of like the base 2 representation of a model number tells you about which model it actually is. Because one of these models is really defined by these 3 different possible kinds of edges. Like I said, cousin edges, uncle edges, and umbilical edges. And really by turning each of these on or off, i.e. by associating each of these with 0 or 1, we define one of these particular models. So there are 2 to the power of 3 models, and the base 2 representation of a model describes what it is. Okay, so now I want to show you the dynamics of this system here. This one's really quite simple. Can you guess what kind of structure develops from this model? So how do we update a system under this model? Well, basically, the offspring are connected to their parents and the offspring of their parents' neighbours. So basically, when we produce our offspring, we just kind of copy the network structure and then add these kind of umbilical connections across. And so what we actually get developing here, see we have a cube now, and in the next time step we're just going to copy this cube and then add these umbilical connections between corresponding vertices. And so we're really getting a hypercube graph growing out, and it's a lot of things are known about the hypercube. It's a very nice, simple network structure to study. So we know the degree distribution is very simple. There's just 2 to the t vertices of degree t on time step t. The diameter of the network, that's the maximum shortest distance between a pair of vertices, that just increases by 1 every time. And you can also look at the average length between a pair of vertices. So the average length is, if you pick a random pair of vertices, what's the distance between them? And you can show that the average length, in this case, just increases by 1/2 every time. So in this case, we have a network which is growing larger, and it's very regular. Another thing you can look at is the chromatic number of these networks. So the chromatic number of a graph is the number of colours that you need, so that you can paint the graph with these colours in such a way that no 2 vertices of the same colour are linked. And in these cases, it turns out to be quite easy to describe how the chromatic number changes. In these cases here, the chromatic number doesn't change over time. And so even if you evolve the graph for hundreds of time steps and end up with some mind-bogglingly massive structure, it will still have the same chromatic number as the thing that you started with. In model 3, the chromatic number goes up by 1 every time step. And in model 7, it always increases. It doesn't more than double, and we don't have an exact description of it. And you can also study things like the diameter. I mean, there are exact formulas for these things in the paper. I don't want to go into too many details, but suffice to say that in these systems, these notions of distance don't really make sense, because the offspring are not linked to the graph that their parents were part of. They belong to a separate connected component. So in these networks, these notions are really quite meaningless. In these networks here, which have these diagonal kind of uncle edges, the diameter and the average length approach constants. And the reason for that is basically that when you have these vertices having offspring, there's really a kind of equivalent path that that offspring has to any given vertex, to the path that its parent has. So the offspring are not any more kind of distantly spaced from the rest of the vertices as their parents are. And in these networks here, which don't have these diagonal edges, the diameter and average length grow linearly. Okay then, so one can also get formulas for the degree distributions of these different models. Now, I've already discussed a little bit about how the network structure, I basically said for model 1 at least, that if you couldn't understand how that tadpole-shaped graph evolves, if you remember, I said that if you can understand how that thing evolves, you pretty much understand how every network evolves. And in fact, each of these models has a similar kind of feature like that. You see, the fact of the matter is that in each of these systems, you have these networks which develop, but the way that a particular piece of network develops, the thing that grows from a particular piece of a network is really independent of what's happening outside of that piece. More precisely, you can take any subgraph of your thing, you can cut it away, and you can consider its evolution separately, and it will evolve in just the same way. Because really these systems are very simple, and there's no information passing that's necessary to show how these systems evolve. And so what all that basically means is that if you can understand how a single edge evolves under these different models, you basically understand pretty much everything, or most things. So these formulas here give the number of vertices which have degree I in these different networks when you evolve from a single edge for t time steps. So here are the formulas for model 0, 1, 2, 4, 5, 6 and 7. And you can see that in these cases the degree distributions are really pretty simple. But there's one notable exception here, and that's this model 3 here. you'll see that in all the other cases, we have really quite simple formulae for the number of vertices of a given degree on a given degree I on time step t. But for this model 3 here, in fact, we don't have a formula. And if I show you a picture here, you can kind of see why. Because it turns out that, in fact, the degree distribution generated by this model is really immensely complicated. And so, in fact, Jonathan Jordan and myself wrote a paper about this called Further Properties of Reproducing Graphs, where we showed that this degree distribution is actually quite closely related to some sort of partitions and things from number theory. And so, in a sense, one can give an exact description of this degree distribution. But in another sense, we don't really have a very useful formula for it. So I just want to talk about this a little bit. If you plot the degree distributions of each of these other networks, you get a very kind of nice, smooth-looking curve. But in this case here, yes, the whole system is deterministic. So this degree distribution here was generated by a repeatable process. But the curve itself seems to have a remarkably complex form, and it doesn't really look like a sort of one-dimensional object. In particular, it looks like if you change the degree that you're interested in by just 1, then the number of vertices with that degree may vary dramatically. There might be a lot less vertices with degree d plus 1 than the number of vertices with degree d. And this is all quite remarkable because, in fact, there's really quite a simple formula for the way that this system develops. In particular, if you have a vertex of degree x on a given time step, then when you update that system, you end up with a vertex, well, the offspring is going to have degree x plus 1, and the parent is going to have degree 2x plus 1. So that means there's a really simple recursion for generating this degree distribution. I mean, just start with a 0, and at any given time step you have a set of numbers, a set of degrees of all of your vertices, and to get the set on the next time step, you just replace every element x with x plus 1 and 2x plus 1. And if you keep doing that over and over again, you get a set of all the degrees of all the vertices which would be in the network. So there's a really simple process for generating this degree distribution, but it seems highly complex. Okay, so I could say a lot more about these models. I've really skipped over many of the analytic results. Suffice to say, there are many different generalizations that one can make. So I'm going to talk about some specific generalizations in a minute, but I just want to talk about one idea, which is to make these models probabilistic. And so essentially one can, instead of thinking of these 3 different kinds of edges as either being off, i.e. 0, or on, i.e. 1, you can associate them with probabilities. So maybe the offspring are linked to their parents with a probability of 0.7 or something like that. And in fact, Jonathan Jordan has wrote a paper about what kinds of things happen when you do make these systems probabilistic in that way. Anyway, I'd like to talk about a generalization in a different kind of direction, because I think these models do capture these reproducing graph models do capture certain aspects of the development of real-world networks, but in most cases there's a very important effect missing, and that is death. I mean, death has a huge influence on the formation of many different kinds of forms. Certainly in biological systems, of course, mortal individuals will reproduce, but they'll also die, and that has a big effect on things. But also in things like, technological networks, technologies will become obsolete, or even in things like sensor networks, sensors will run out of batteries. So this idea of certain fixed lifespan is kind of important. So now I'm going to talk about how we can include this effect in as simple a way as possible. And that is just to assume that when a vertex's age exceeds a given number, which I call the age cap C, that vertex dies. Okay? So it's basically exactly the same system as before, except the vertices grow older, and once a vertex has lived more than C time steps, it gets destroyed. Okay, so what are the effects of introducing mortality? Well, I'm going to talk about them in more detail, but basically the first thing is that what we actually have is really a subgraph of what we get in the case with pure growth. And that's nice because, although I didn't discuss it too much before, we have some rather powerful techniques for understanding the kinds of structures which are generated by the pure growth models. In particular, one can introduce binary strings so that whenever we update the system, we put a 1 on the end of the name of every parent, and we give the offspring the same name as its parent, but with a 0 on the end. And so we use binary strings to keep track of the different vertices in our system, and then actually we can get exact results we can get exact descriptions of the vertex sets and edge sets of the networks which are developed. So we've got some really powerful techniques for analysing the kinds of structures which develop in the pure reproduction models. And the thing is that here, when we introduce mortality, the important thing is that what we get is just a kind of substructure of what we got in the pure case, because we've pretty much got some of the same things, but some of the vertices aren't there because they or their ancestors have died of old age. And also, the networks we get, they tend to have a faster growing diameter and average length. So these networks tend to be longer. And the reason for that, sort of basically, is that the vertices in the middle tend to be the older vertices, and they tend to be dead in these models. And another thing is we tend to have more widely spaced degree distributions. Okay, now, so as I've said before, the way these age cap systems evolve is really intimately related with things like Fibonacci numbers, and also with the golden ratio. So the thing is that, just for a start, let's forget about the edges. Let's just think about how the population of vertices evolves. So what about the simplest case, when we set our age cap C to be equal to 1? Well, in this case, when we update our system, we increase the age of every vertex, and then we give every vertex a age 0 offspring, and then we destroy every vertex of age greater than the age cap, which is 1. And so, in fact, what we get is that the number of vertices on a given time step are given by Fibonacci numbers. So, you've probably heard of the Fibonacci numbers. They're very famous. The idea is that the next term in the sequence is determined by getting the current term in the sequence and adding the previous term in the sequence. So 5 plus 3 is 8, so the term after 5 is 8. And this is really kind of nice. In the old models, the number of vertices doubled every time step. But now, in this system, at the limits, the number of vertices on the next time step is equal to the golden ratio times the number of vertices in the current time step. So I always get a little thrill when I see the golden ratio appear in models, because it's really such a magical number. I mean, it appears in the spirals of seashells and sunflowers and the Milky Way. It appears in lots of different proportions of a well-formed human body. Leonardo da Vinci sketched it into his masterpieces. It's a really, really beautiful number that appears in many places within science and mathematics and art. Okay, so what about more generally? What about when we have our age cap equal to C? You know, maybe C doesn't equal 1, in other words. So in the more general case, where we have a general age cap C, the way the number of vertices evolves in these systems is really described by kind of generalization of the Fibonacci numbers. Basically, this is known as the Leslie population model. So this is quite an old model from population biology. And basically it works like this. We let this thing here, this NIT, we let this denote the number of vertices of age I at time t. And so we imagine that we have different vertices of different integer ages. And basically the state of the system at time t is given by describing the number of vertices of all the different ages at time t. And so we have this kind of vector here, n0t, n1t, n2t, etc., which describes the state of the system in time t. Now, in the context of our systems, we can think of nit as the number of vertices of age t at time step t. Of the number of vertices of age I at time step t, sorry. Now, the idea behind the Leslie matrix model is really quite simple. Basically, to get the state vector on the next time step, we just multiply this state vector at the current time step by this thing called the Leslie matrix here. Actually, this is just a special kind of Leslie matrix. Basically, the idea is that we have these fertility rates across the top. And these tell you how many different, so here you put how many different offspring these vertices of different ages will have. And in this kind of off diagonal here, you put the survival rates, which are the probabilities that a vertex of a given age survives until the next age. And we take it as implicit that once a vertex reaches age C, it kind of dies the next time step. And so the basic idea is that the population vector on the next time step can just be obtained by multiplying by this matrix here at the current time step. And this is really nice because basically the laws of matrix multiplication just make this drop out. It just makes it work. And you can actually do a lot of analysis, linear algebra and things like that, to determine things like what are the asymptotic growth rates of these systems and what are the principal eigenvalues and associated eigenvectors, and how many individuals will there be of different ages asymptotically. Basically, you can understand a lot about the population of vertices and what ages they're going to be. And this all pretty much drops out because essentially in our systems, in each of our systems, the way the population of vertices evolves is described exactly by this kind of special case of the Leslie population model. So this really describes how the vertices evolve and what different ages they'll have. But of course we have an extra feature. Our vertices are not just floating in free space like the ones assumed in the Leslie population model, because our vertices are interconnected and we have these different rules for how the offspring are forming links. And so now we understand how the population of vertices evolves, we can go back and think more about what happens to the edges. So in fact there's a lot of results I have about how these age cap systems evolve. One can get lots of things like degree distributions and studies of various different graph invariants, and just here I show the asymptotic growth rates of a number of edges. So these are in all the different models, and these are for different age caps. And the sort of asymptotic limit when you make the age cap infinity is the pure reproduction models, because in this case the vertices live forever. But anyway, these are just numbers here, but I actually have explicit formulas for each of these things. I just didn't want to put too much mathematical notation into this talk. You can find these kind of things in the paper. Anyway, So one can do quite a lot of analysis on these systems, but also when one adds this idea of death, or culling, if you like, into these kind of systems, one sees many other interesting effects start to occur. For example, you can have these systems. Look at model, this is model 2 here, and let's just see this thing evolving on this age cap model. So, as I've already said, an update just consists of giving every vertex an age 0 offspring and increasing the age of every other vertex. So, let's update this system. Every vertex has an age 0 offspring. Well, sorry, every vertex gets one step older, and then they have an age 0 offspring. The thing is now, our age cap is equal to 2. So every vertex whose age exceeds 2 gets destroyed within the updating process. So there we go. This vertex is now too old, and they're going to get culled. So they get removed from the network. But you see now, we've just seen something fairly interesting happen, because look what kinds of things we have now. Our network, our tree structure, is now broken into 3 different parts. And what's even more interesting is that this part looks like our initial network, this part looks like the network we had on the first time step, and this part looks like the network we had on the second time step. So let's evolve the system again. So, of course, these parts continue to self-replicate. And so this is fairly interesting. This is a new kind of behavior. When we introduce culling into these systems, we can see self-replicating structures emerging. And so a good question then is, how are these systems reproducing? Can their kind of behavior be characterized? Well, it turns out that it can in a fairly simple way. We can draw this kind of flow diagram or phase diagram, which shows how these different structures make each other. So one of these gets updated to make one of these, this gets updated to make one of these, and then when you update this, it breaks into one copy of this, one copy of this, and one copy of itself. And so now we have this kind of phase diagram here. We can really understand how the system works. In fact, if you're interested in, say, the asymptotic number of connected components, you could just have to look at what's known as the adjacency matrix of this phase diagram. That's over here, and it's fairly interesting actually, because this is just the transpose of the Leslie matrix. And so what this actually means is that really you're not getting far away from your Leslie matrices here. It's almost as if however this model got cooked up in the Platonic mind, or whatever you want to think of it, it's not really very creative. It just keeps going back and back to the Leslie matrix, and it seems to use it to derive all of its complexity. Anyway, the asymptotic growth rate of a number of connected components is just given by this number here, and this is known as this is a kind of generalization of golden ratio. It's the growth rate of generalized Fibonacci numbers. Anyway, so that's a little bit about these systems here, which have these age caps. So that's one way that you can introduce mortality into these kind of systems. Okay, so now I want to talk about how we can include death into our reproducing graph models using game theory. So this is really a very simple idea. The basic idea is just that now we assume that our vertices have different strategies associated with them. So a good way to think of these strategies would be as, say, different kinds of animals. So, vertices using the red strategy have offspring who are using the red strategy, in much the same way as lions have offspring which are also lions. And so the idea is that we have these kind of strategies and connections being inherited by the offspring, and we also have an extra feature, which is that unfit vertices die. So in the age cap systems, it was the old vertices that were dying, but now it's the vertices which perform poorly in the strategic interactions with their neighbours that die. Let me see if I can explain in more detail. So I guess the best way is with an example. So here we've got a payoff matrix here. This here is really essentially defining a game. So what this means here is that if we use the red strategy against somebody who uses the blue strategy, we get a payoff of 2. If we use the red strategy against someone who uses the red strategy, we get a payoff of 0. If we use the blue against someone who uses a red, we get a payoff of 1. If we use blue against someone who uses blue, we get a payoff of 3. Okay? So this tells us which payoff we get against a game with somebody else. Okay? So what we're going to assume now is we're going to assume that this payoff matrix defines how everybody gets payoffs. So whoever they are, whoever they're playing against, if they want to figure out what payoff they get, they just use this matrix. They say, which strategy did I use? Which strategy did they use? Okay, my payoff is this. Alright? So this is basically defining a game. Now the idea behind our system is we have a graph, and the different vertices are using different strategies. Like here, we've got a couple of guys using the blue strategy, and one guy using the red strategy down here. And the idea is that these vertices here, they play games with their neighbours on the network structure. So wherever a guy is linked to another guy, those two are going to play games with each other, and they're going to get payoffs that depend on which strategies they are using. So, for example, this guy here, in this situation, they're going to get a total payoff of 3 plus 1. Why? Well, because they score a payoff of 3 by interacting with this guy at the top, and they score a payoff of 1 by playing against this guy at the bottom. So, total payoff is really our notion of fitness. We think of those two things as synonymous, okay? And so the way our systems works is as follows. An update is a two-stage process. I'm going to talk about model 1 because it's a nice simple one, okay? So under this one, the reproduction stage is, as before, every vertex has an offspring with the same neighbourhood as its parents and the same strategy. So this is what we get after we do the reproduction stage. The parents, the offspring inherit their parents' neighbourhood and strategy in much a similar way as animal offspring have a similar type and similar surroundings to their parents. So this is stage 1, the reproduction stage, and then we also have, and so what we do now, we have the killing stage. So what do we do here? Well, we calculate the total payoff that every vertex gets, and then we assume that we've got some kind of threshold. So this threshold, this is just a number, okay? In this case, we'll set it as 4. And the idea is that what we do then is we kill every vertex which has a total payoff less than this threshold, okay? So we kill these two vertices during this killing stage, and this is the resultant graph, okay? So this is actually the network we get after the first update. Right, so let me go through this again. An update consists of a reproduction stage and a killing stage, okay? So if we want to think of these things as biologically inspired, we can think of the reproduction stage as something like spring, when offspring produce individuals who have a similar strategy and surroundings to their parents. And then we have a killing stage where animals which do not achieve a certain level of fitness are destroyed. So we can think of that as something like the winter time, when harsh conditions eradicate all the animals that don't achieve a certain level of fitness. And in that context, the entire update would be equivalent to the passage of a year, say. So this is just an ecosystem-based interpretation of this. Of course, there are different models, and one can give different interpretations. Anyway, a good question is, how do these kind of game-based systems evolve? Well, I can tell you that they can be a lot more complicated than the things that I've talked about before. Why? Well, because now we actually have interaction between the vertices. They're not just following their own life processes, independent of what the other ones are doing. Now our vertices are really interacting. And in fact, we can just look at a very simple case and we can really uncover remarkable dynamics. I'd say that maybe in my time as a researcher, which has now been about 4 or 5 years, this is certainly the most surprising system which I've ever encountered. So basically, this is a very simple example where we just have a one strategy game. If that isn't a contradiction in terms, we have a one strategy game, okay? So we assume that every vertex uses this red strategy here, and this has a payoff of -1 against itself, okay? So what does this mean? This means that basically it's a bad thing to have too many neighbors, because you're always going to be playing these so-called games with your neighbors when you always score a payoff of -1. So the more neighbors you have, the lower your payoff is going to be. And we're also going to assume that our threshold value here is equal to -d, where d is some natural number. And so how do these systems work? Well, basically, we can give them the following interpretation. In these systems, an update just consists of giving every vertex an offspring with the same neighborhood as its parent, and then destroying every vertex which has more than d connections. So these systems are really very, very simple in the way that they run. And basically, the way that they work is that having a high degree is bad. So one kind of interpretation of these, you can think of them sort of like a ecosystem evolving with some kind of resource shortages, okay? So if you imagine these things to be an ecosystem, when a individual is interacting with too many other individuals, they'll be sharing their resources, maybe their food, with too many other individuals, and they won't be able to support themselves anymore, and they will die. So this is the kind of rough biological interpretation of these kind of systems. Okay, so I'll use this Mathematica worksheet to show you how this system evolves. So we start off with just this 2-vertex complete graph, this simple thing, and we keep updating it. So as I've said, each update consists of giving every vertex an offspring with the same neighborhood as a parent, and then destroying every vertex that has more than 4 connections. So after one update, we just have this kind of length 3 path here. So let's update the system again. Well, the net effect of our next update is just to give every vertex an offspring with the same neighborhood as the parent. So now we have this structure here. It's kind of a hexagon with a kind of diameter chord and a couple of arms sticking out of it. So now we update the system again. We give every vertex an offspring with the same neighborhood as the parent, and then we destroy every vertex which has more than 4 connections. So the net effect of those two operations it gives us the updated structure, which looks like this. And so what is this? Well, we've got a hexagon here with 6 legs, so I guess it's kind of like an insect or something, or maybe like a butane molecule, if you like hydrocarbons. And we've also got a couple of vertices, which are kind of floating free. And so what happens when we update this system again? It looks pretty interesting. Well, when we update the system again, the system actually breaks into 6 different lines. Okay? So that was quite unexpected. And then as we update the system more, we see that these lines are going to grow and break into more different structures. So these degree cap reproduction systems are really tending to have highly complicated quite complicated dynamics. It's remarkable that we get these self-replicating structures from these very simple rules. Of course, we did see self-replication happening before within the degree cap systems, but what's interesting about within the age cap system, but what's interesting about the degree cap systems is that you can actually find some really complicated behavior. So what about if we increase our degree cap now? So let's set our system back to 0 and we'll pump up the degree cap to 6. Okay, so we're going to start the system evolving again. Remember, each update has 2 stages. The first stage is the reproduction stage, where vertices have offspring who inherit their parents' neighbourhoods. And the second stage is the killing stage, where we destroy vertices which have more than 6 connections. Okay, so in a way this is kind of like Conway's Game of Life. Anyway, so we evolve the system, updating and updating again. It looks similar to it did before, and updating again, similar to before, and now we'll update again, and instead of breaking up, now the system can grow a bit larger because the degree cap is bigger. And so now this is the network that we have. And if we update again, it gets more complicated, and then it breaks up into several pieces. And if we just keep evolving the thing, we see some kind of interesting stuff happen. Because now we've actually got a variety of different structures. We have singletons, and we have these kind of funny things that grow from hexagons, and we also, if it's, maybe this is a bit too small, make it bigger, we also have some of these 3 paths here. So we have 3 different types of vertices, 3 different types of graph structures here. Which is quite surprising, I would say. There we are. So there's a 4 vertex path here. So that kind of shows that we have 2 kind of non-trivial graph structures. So what's going on here? How are we getting all these different structures from our single initial thing by following these simple rules? And what exactly is going on? Well, to understand more about what kinds of things are happening within these degree cap reproduction systems, we can make these kind of phase diagrams here, which show what kind of things get produced when we update various different graph structures. So for this case here, the degree cap's equal to 2. Now the arrows pointing out of a given structure point towards all the different connected things that get made when we update that structure, as in when we do a reproduction stage and a killing stage. So for example, when we update this thing here, we get 1 of these. When we update this thing here, we get 2 of these and 2 of these. And when we update these isolated vertices, they just copy themselves. There's no edges there. And so using these phase diagrams gives us a nice, simple way to summarize what's going on with these different things. Anyway, when we make our degree cap equal to 4, we get a more complicated kind of chain of self-replication here. This little structure grows up and grows up and grows up into this, kind of butane-shaped graph here, and this then breaks into 6 more copies of this. It also makes some isolated vertices, but I'm not showing isolated vertices in these kind of diagrams because it makes them too cluttered. But what gets really interesting, as I just showed you with a simulation, is what happens when we have a larger degree cap, like here. I mean, we still get self-replicating structures, but we get much more variety and much more complexity in the way the system evolves and the way that this self-replication actually ensues. So let's try and keep track of what's actually going on here. We start off with this 2-vertex graph. This is our input, and we just keep updating it according to that simple rule. Give every vertex an offspring with the same neighbourhood as a parent, and then destroy every vertex which has more than 6 connections. Okay, so when we do that, we see that this graph here creates 1 of these, something a bit bigger, and this gets bigger again, and this gets bigger again, and we get this kind of butane-shaped molecule, butane-shaped graph here. Now, when we update this, we get this network structure here, and then this one, and this is now sort of, in a sense, too big. It has so many vertices, it's just about to burst. And when we update this thing again, it actually breaks into 6 copies of these kind of cross-shaped things here. And when we update these, they get a bit bigger, and then they break into, and then they make these funny things here. And this is the interesting point here, because when we update this, we get one copy of our original graph for each of these. And in fact, if this is our first iteration, we'll have 6 of these already. So we're already seeing this is self-replicating, because we had one of these, and then after 1, 2, 3, 4, 5, 6, 7, 8, 9 updates, we've now got 6 of them. So we're having self-replication, but also this is going to make 3 copies of these. So we've really got 2 different things going on here. We have self-replication, but we also have an increase in the variety of different forms. So this is almost like the situation, I suppose, which happened on Earth, where we started off with a single amoeba, and then we ended up with lots of different kinds of self-replicating organisms, such as fish and mammals and plants and all the other things. Okay, so in a way, there's some kind of parallels between these systems and those, because what's remarkable is, when you increase the degree cap even further, you start to encounter dynamics of absolutely bewildering complexity. I mean, this is exactly the same situation as before, except for one little difference, and that is that now our degree cap is just a little bit higher. So now our degree cap is equal to 8. So an update is now give every vertex an offspring with the same neighbourhood as the parent and destroy every vertex with more than 8 connections. Phew. Okay. But what's amazing now is that the phase diagram, you know, the kind of diagram like this that shows which structures make the other structures, is amazingly complicated. It has thousands of different nodes, because just from evolving this tiny little graph here with 2 vertices under this rule, we actually get thousands of different kinds of structures which grow and change and self-replicate and create different copies of themselves. Some of these individual structures have thousands of vertices, and so it's really almost as if one has got an entire ecosystem of different self-replicating structures just from having a single little structure and following a very simple biologically inspired rule. This is the network structure you have when the degree cap is equal to 10, and it's even more complicated. And also, strangely, it's kind of different to the others. In this case, unlike the previous cases with lower degree caps, we actually have that the 2 vertex complete graph does not self-replicate. It grows into something else, and that something else starts self-replicating. And now we have tens of thousands of different kinds of structures which are all growing and changing and self-replicating. And to be quite honest, I do see this as relatively analogous to starting off with a single amoeba and then ending up growing an entire civilization, ecosystem, etc. Anyway, as I say, this is probably some of the most amazing things which I've really found. I think it's very extraordinary. Number 1, how easily you can get self-replication from these systems. Number 2, how easily you can get complexity. And number 3, how surprising the dynamics of a very, very simple kind of procedure can be. There's many kind of questions you can ask after you've seen those kind of things. One thing that people say often when they see these kind of deterministic processes which have complex behavior is, what happens if you add randomness? I mean, sometimes if you take away the determinism and you add randomness, you can kind of stop the interesting things from happening. And this is possible sometimes in cellular automata, for example. And so an interesting question here is, do you still get this kind of lifelike self-replication and creation of complexity if you stop the system being deterministic and make it random? Well, I investigated this issue a little bit. I considered the case where the vertices only reproduce with a given probability, and when the vertices of high degree only get killed with a certain probability. And indeed, in this case, we still get the complex self-replication. So it's kind of interesting. Well, okay, that was just a little bit about one of these particular models. all the things I've been talking about so far regarding game theory based reproduction were all about this model 1 here, where the offspring are born with their parents' neighbourhood. Now, of course, we can look at a similar question for all of these other different models, and of course we can really study the whole game-based system, game-based reproduction for all of these different models. And it turns out that in most cases, one can really do some fairly good analysis and understand quite a lot. But there are these two cases here, with Model 1 and Model 3 as well, where we can really see immense complexity, and that's a kind of double-edged thing. On the negative side, these things can be too complicated to explain analytically, but on the positive side, we can find all this immensely rich and fascinating behaviour, like the self-replication. Anyway, if you use the other kind of reproduction models, it tends to be a lot easier to understand what's going on, even in generic games. Okay, so what I'm showing here is a similar kind of phase diagram. So this is very similar to the kind of degree cap reproduction thing that I showed you before. The difference is that this is for Model 3 here. So now the difference is that our offspring are born linked to their parents, neighbours and their parents. So, it's a bit different. And also, we're just starting with a single vertex here. So we have even simpler initial conditions. And qualitatively, this kind of behaviour is really quite similar to the one we saw before. By the way, there's many interesting open questions about these degree cap reproduction models. Some questions which I've worked on for a long time, and I really would like to see some answers to them. In particular, I don't know, if you start with a finite structure, is it always true that only a finite number of structures are produced? Or is it possible for something to grow forever and stay connected? I think that's a very interesting question. I don't know the answer. It seems a very difficult question as well. Well, anyway, as I've said, one can consider different kinds of models, there's 8 different reproduction models. So one can consider what happens if one uses different models. And if one applies this kind of game theoretic framework, one can really often get quite easy results to understand. So in contrast to these kind of systems, which are very complicated, if one uses a different kind of growth mechanism, like growth mechanism 5 here, where the offspring are born connected to their parents' neighbours and their parents' neighbours' offspring, we can really understand these game-based dynamics pretty easily. So let me just remind you what these game-based dynamics how they work. Basically, they work so that the offspring get their parents' strategies, and then we have this killing stage where we kill every vertex who has a total payoff, or fitness, which is less than this number t. Well, the thing is that under this kind of growth mechanism here, we can really do a special trick which allows us to make these games look a lot simpler, because the key observation here is that the offspring are really kind of automorphically equivalent to their parents. In other words, in the updated structure after the reproduction stage, the offspring pretty much look the same as their parents. They're almost indistinguishable. They have the same strategy and they have the same structural standing within the network. And this kind of symmetry really allows us to do a special trick. That trick is basically that, the way these systems work is that we do reproduce, kill, reproduce, kill, reproduce, kill. So we're applying these two different operators, if you like, the reproduction operator and the killing operator. We're applying those alternately. But what we can do is we can switch around the order that we apply these operators. So we can basically find an equivalent kind of thing where we just do all our killing at the beginning with different modified thresholds, and then we do our reproduction at the end. So you can see from the algebra here. Basically what I mean is that rather than updating the graph several times, you can just do a load of killing at the beginning and then do reproduction later on. And the fact that you can do this, the fact that these operators almost commute, if you like, really gives you a different way to understand the system. Because basically, for a generic game, you can just do an equivalent kind of evolution process where you kill a load of stuff at the beginning, and then whatever doesn't get killed, you know is going to grow forever. So there's a definite benefit from doing this kind of juxtaposition of the reproduction and killing operations, which really allows a simplification of the system. And this kind of thing's possible for each of these growth mechanisms where the offspring looks similar to their parents, as in these ones here. And I'd say that pretty much all of these systems, except for these in the orange circle here, can be understood pretty easily, even when you're running sort of general games on them. Well, that's pretty much the end of this talk now. And I'd say these systems are inspired by game theory. I think that they have something to do with network design. I think that these kind of systems do open an interesting kind of door to thinking about network design, because the whole idea of sort of rewarding or punishing certain parts of a network for growing in a certain way could turn out to be a fairly useful and interesting way to produce networks which have forms which we like, or to keep networks persisting in a certain way. I mean, I'd say that this almost naturally happens in things like economic networks, where inefficient pieces of the network are getting destroyed. And my favourite kind of potential application of these systems is actually seeing if you can use something like this to make self-replicating structures. I think that self-replication is one of these technologies which I don't see it can't be too far away. I can't see it being too long before we can make artificial self-replicating machines. And I think when one looks at systems like this, one can see that, particularly with adaptive graph models, it's really quite easy to achieve self-replication. And self-replication is a very interesting thing, because if you want something to be a self-replicator, ultimately you want that thing to be pretty simple, because if it's a really complicated thing, then it's going to have a hard time building itself. And so, you know, this whole idea of kind of just looking at the dynamics of very simple kinds of systems is probably going to be useful for finding self-replicators. Right, so that's pretty much the end of my talk. I'm Richard Southwell. Thank you for your attention.